This session will introduce the other two types of modern synthesis methods and the evaluation metrics in speech synthesis. The two primary technologies generating synthesized speech waveforms are concatenative synthesis and formant synthesis. Then, a trainable TTS system based on HMM model was established at the end of 1990. Nowadays, deep neural networks has been widely used in TTS. In this session, we mainly introduce the traditional techniques, concatenative synthesis and HM-based synthesis. Formant synthesis was a main TTS technique until the early or mid-1990s, when increasing memory size and CPU speed allowed concatenative synthesis to be a reliable approach. The idea of concatenative synthesis is based on the concatenation of stringing together of segments of recorded speech, recording the small units of speech, for example, a diphthong unit, and glues these units together to form words and sentences. Generally, concatenative synthesis tends to sound more natural than formant synthesis. The speech of a voiced talent is recorded and stored after digitizing. At synthesis time, the computer produces the target speech by cutting out segments from the recording and concatenating them according to a certain scheme. There are mainly two types of concatenative synthesis methods: diphthong synthesis, which is the most common option, and unit selection synthesis. Diphthong synthesis uses a minimal speech database containing all the diphthongs, sound-to-sound transitions occurring in the language. The region of speech unit stretches from the middle of one phoneme to the middle of the next phoneme. The figure shows diphthong boundaries in stops. Generally, the middle of each phone is steady state. This method records one speaker saying each diphthong. At runtime, the target prosody of a sentence is superimposed on these minimal units by means of digital speech signal processing techniques, such as LPC, ASOLA, pitch, synchronous overlap and add, and MBROLA, multi-band overlap and add. Here are two sound examples. One is the results by combination of LPC and diphthong synthesis in the early year 1977.
This paper describes a small real-time speech synthesizer. The synthesizer requires as its input a string of phonemes and the associated duration, pitch, and amplitude parameters.
In the year 1996, more efforts were done with the MBROLA synthesizer.
It would be a considerable invention indeed, that of a machine able to mimic our speech with its sounds and articulations. I think it's not impossible.
Alice was beginning to get very tired of sitting by her sister on the bank.
Contemporary concatenative speech synthesizer use variable unit selection. Unit selection synthesis uses large database of recorded speech. During database creation, each recorded utterance is segmented into some or all of the following: individual phones, diphones, half phones, syllables, morphemes, words, phrase, and sentences. At runtime, the desired target utterance is created by determining the best chain or candidate units from the database, that is, unit selection. This method may record 10 hours or more, so have multiple copies of each unit. It uses searching algorithm to find the best sequence of units. For example, a specially weighted decision tree. Unit selection provides the greatest naturalness of synthesized speech. However, maximum naturalness typically requires unit selection speech databases to be very large. Here are two examples of synthesized voices tailored to the particular speakers using unit selection synthesis method.
Tell me what you think that I said.
Tell me what you think that I said.
HMM-based synthesis is a synthesis method based on hidden Markov model, which is a kind of statistical parametric synthesis. In HMM-based text-to-speech systems, HTS system, the frequency spectrum, vocal tract, fundamental frequency, voice source, and duration prosody of speech are modeled simultaneously by HMM. Speech waveforms are generated from HMM themselves based on maximum likelihood criterion. This method firstly generates the most likely sequence of spectra, for example, MFCC and excitation F0 parameters for the given phone sequence using HMM training, and creates a filter using the spectral parameters. The synthesis procedure passes the excitation parameters F0 and noise through the filter to generate the waveform. The advantage of HMM-based speech synthesis is that this technique only requires the model parameters to be stored and not the speech data itself. In addition, HMM-based synthesis requires less computation than unit selection. HMM-based synthesis has the potential to synthesize the high-quality speech mainly because it can produce continuous spectral contours as opposed to unit selection synthesis. Thus, this method can operate at much lower expenses in real-time application. The figure shows the block diagram of HMM-based synthesis by Zhang and Toda in the year 2005, which includes training part and synthesis part. Speech synthesis needs to extract F0, which represents the excitation parameters, and MFCC features, which are spectral parameters, and extract annotation information of the relative test, that is label, to train the HM model. For new sentences, the synthesis part need to extract the annotation information by text analysis firstly, and then input it into the HMM model to generate acoustic parameters, F0, MMCC, and so on. Finally, use the algorithm like Straight or other algorithms to restore these parameters to synthesize the speech. This is done by generating an excitation and filtering it by means of the spectral features on a frame-by-frame basis. It is usually necessary to convert the text into pronunciation units first, and the smallest units are called phonemes. Each model represents a phone or a subphone, diphone, triphone, and so on. Each model consists of multiple states. The current general model divides a phoneme into 3 states, which are used to simulate the beginning, duration, and end of the phoneme. Thus, a 3-state model is used to represent the phoneme. Each Gaussian mixture represented by a different state with the transition probability as the mixture weight. Each state emits spectral and F0 feature vector. In speech synthesis, the process of HM model in speech recognition has to be reversed. Here, we give the word sequence and search for optimal sequence of feature vectors. There is another method, HM-based hybrid synthesis, which combines concatenative and HM-based synthesis. Given a big database, this method aims to find a string of units that maximizes probability of HMM and then uses phone concatenation to improve speech synthesis quality for natural speech. Intrasegment scores can be pre-computed, and concatenation scores could also be pre-computed. There will be good job at concatenation matching. Also, the prosody is established by HMM. The hybrid speech synthesis system combines 2 advantages. On the one hand, it uses real speech segments to splice and synthesis, and the synthesized speech has high sound quality. On the other hand, it combines the HMM model trained by statistical parameter method to guide the selection of phones, and the overall prosody of the synthesized speech is relatively stable. The consistent evaluation of speech synthesis systems may be difficult because of a lack of universally agreed objective evaluation criteria. Different organizations often use different speech data. For speech synthesis, intelligibility is a basic requirement, and high naturalness is the goal pursued by practical applications. The evaluation of synthesized speech often uses subjective test methods. Intelligibility tests use diagnostic rhyme test, DRT method. Humans do listening identification choice between 2 words differing by a single phonetic feature. The percent of right answers is intelligibility score. Overall quality tests use mean opinion score, MOS, test method. Listeners vote on a scale from 1 bad to 5 excellent. In preference tests, listeners compare 2 speech samples to prefer A or prefer B. That's all for this session. See you next session.